So this chapter is going to cover the chi-square test. I'm going to go over the basics of this test. So when you're studying the book, just really focus on what the chi-square test is, what it's looking at, and what it does. Normally, I would teach the class how to actually do it, like with a calculator and run the stats. But because of this remote method, we're going to skip that. I'm just going to have you guys really focus on the understanding of what this test is. So be able to identify the test, how you use it, and what it means. So I'll go over that in this presentation. I also put up some links, some videos you guys can watch on the internet that'll also help you with this. Okay, so chi-square is a non-parametric test of significance used with discrete level variables. So what that means is non-parametric means that we're just dealing with frequencies. Okay, so make sure you know that. 25 women, 68 men. 38 juniors, 48 seniors. That's non-parametric data. What that means is there's no bell curve, there's no means, there's no standard deviations, there's no variance, there's none of that. It's just counts, how many. Okay, so that's why it's called non-parametric. There's no parameters, meaning you don't know things like mean scores, like the tallest, the shortest. We don't have anything like that. So remember, you use chi-square with discrete level variables. That is nominal and ordinal. Do not use chi-square with interval or ratio level data. There's too many problems doing it with ratio and interval level data. This test is not designed for that kind of data. You'll also notice that there's just way too many cells that you can have. Remember chi-square, remember we went over in class like 2x2 tables? There's no such thing as a 2x2 table when you're looking at things like how many push-ups people can do and you have 500 people in the study. You know, if you're like looking at different variables, you can wind up having like 400 cells in that table. And you have to have a minimum number of people in each cell. Okay, you can't have like zeros, ones, and twos in each cell, meaning you can't have one junior that can do 10 push-ups because you can't run parametric or statistical tests with that few people. So remember, chi-square is designed for nominal and ordinal level variables where you have a limited number of cells. Again, remember the 2x2 cell that we talked about. I'll show you some examples as we move through this. So what is the chi-square test doing? It's a non-parametric test that just looks at counts. What that means is it just looks at how many people fall into each cell in the table. So you see here on the slide it says the test looks to see if the expected frequencies differ significantly from the observed frequencies. Okay, observed frequencies is what you actually get. Again, I'll go into more detail and when we get to some of the slides here. That's what the O means. So if you have, for instance, in a class, 5 juniors that smoke cigarettes, that's your observed frequency. If you expected to have 10, that would be your E, or your expected frequencies. Now, what chi-square does is it looks at the difference between those O's and the E's. And again, just hold on a minute, you'll understand this better when I show you some examples. If the difference is, if those O's deviate enough from the E's, in other words, if our observations differ enough from what we would expect to find, we'll reject the null hypothesis and say these groups are not the same. So let's break this down. The expected frequencies is what we would expect if there were no differences. So the E's represent the null hypothesis. In other words, if there were no differences between women and men in terms of how much they smoke, the frequencies we get between them should be the same. In other words, if we ask 50 women if they smoke and 25 say no, then when we ask 50 men if they smoke, we would expect about 25 to say no if there are no differences, no gender differences in terms of smoking. That would be the E. But when we ask men, do you smoke? Let's say, for instance, let's just make this up and say 25 say yes. And then we ask the women, do you smoke? And only 10 of them say yes. That's a difference of 15. Is that difference enough for us to be confident that these groups are different? In other words, are those O's far enough away from those E's for us to be confident and reject the null? Remember, the O's sort of signify the alternative hypothesis, the E's signify the null. And you want those O's as far away from those E's as possible for you to be confident to say that these groups aren't the same. Here's the formula for chi-square. Again, you'll see all this in your text. This x with a 2 above it, that's the symbol for chi-square. That e is the sum. Again, I would show you guys normally how to do this formula. It's pretty simple. It just counts. You're just taking those observations, subtracting the e, squaring them, dividing by what you would expect to find. And if that chi-square value, which is the test statistic, is large enough, in other words, if that test statistic is larger than the statistic in the table, you will reject the null hypothesis and you will say that we found differences between these groups. Okay, we'll go and do an example right here and you understand what this is a little bit better. So this is the basic formula. It's pretty simple. Remember, it just counts. How many? That's all it is. Okay, so here's an example right here. Let's say you ask somebody, are you a part-time or a full-time student? Do you have children? So what you're doing is, the reason this is a crosstabs, because remember, you're crossing the cells. So we have two variables here. Are you a full-time student or a part-time student? So we have full-time and part-time. The idea is you can't be both. Remember, that's what discrete variables are. You're either full-time or you're part-time. And then do you have children? Yes or no? Okay, so these are both nominal level variables. They're both discrete. So in other words, let's say we ask somebody named Julie, are you a full-time or a part-time student? And she says, I'm full-time. Okay, if she's full-time, then we know we're in this top row right here. If you say, now, do you have children? And she says no, then she would go right here at the crosstab where full-time crosses with no. And then let's say, for instance, now we'd have 170. Let's say if we added one more person, instead of 169, now it would say 170. Okay, if you asked like, if you asked Juan and he said, are you full-time or part-time? And he said, I'm part-time. You go, do you have children? And he said, yes. Then obviously he would go in the lower left cell right here. And remember, guys, keep this in mind. This is a 2x2 table, 2 rows, 2 columns. This over here where it says total, remember, this is a margin. This is not a part of the table in terms of the cells. And here at the bottom where it says count expected and it says 46, 46, 183, 183, these are margin totals. And there's 229 people in this study total. Now what chi-square is going to be looking at is very straightforward. The counts are the O's. So that means 31 people are full-time with children. That's the O. Here's what we would expect to find if there were no differences. We would expect to find or to have 40.2. Now, I'm not going to show you guys how to get these numbers because, again, I'm not going to expect you to do this. I'm not going to ask you how to do the formulas for this for any quizzes that come up. But just note that what it is. So what it's saying is this 40.2 or far enough away from this 31 for us to be confident that there's something going on here? Is this 5.8 far enough away from this 15? Is this 23.2 far enough away from this 14? Is this 159.8 far enough away from this 169? Remember, the bigger the distance between these O's and these E's, meaning the bigger the difference between this 31, yes, and this 42, the bigger that difference right there, the more likely that there is a significant difference. In other words, in a situation like this, you're looking to see if full-time students are more or less likely to have children, or are part-time students more or less likely to have children. And what we can see here is clearly full-time students don't have kids. Look at that. There's 168 here. That's a lot. So obviously there's a lot more than part-time. Part-time, we can see that bulk of the students here overall generally don't have children. But what we can see here is that full-time students are much more likely to have children than part-time students. They're twice as likely to have children. Okay, so what you're going to find here, if you were to actually run this data, is you would come up with that chi-square value, and you would get a table value, and you would see if that table value is bigger, bigger or smaller than the critical value. Okay, so once again, you're going to get a chi-square value. You're going to compare that to the table value to see what your decision is going to be, and I'll show you an example of that right now. Again, if you look at the arts, you can see 53% are in the upper. So again, are people that come from wealthier backgrounds more likely to major in the arts? Okay, if you look here at the bottom, the first two are descriptive. This is just descriptive. This one's the inferential table at the bottom. This is the chi-square test. Now what you see here is you see a chi-square value. See where it says Pearson's chi-square. You get a value of 36.7. That's actually a big chi-square. That's a big chi-square value. The bigger that value is, the more likely these groups aren't the same. Okay, so just kind of keep that in mind. And right here we have what? If you look at this, we have a 3 by 4. So we have 1, 2, 3, 4, 5, 6. I'm looking at the middle table. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's 12 cells here. This is a 3 by 4 table. Remember, don't count the margins. Where it says total on the far right and the lower row where it says total, those are margins. That's not the crosstabs. The crosstabs are where the observed frequencies are, right here. So this is a 3, meaning 3 rows, 4 columns. 3 by 4, 12 cells. Okay, so I'm not going to go so much into degrees of freedom. That's a more complicated concept. But all that means is how many of these cells here, how many values in here are free to vary. It just says 6. It means out of these 12, 6 of these numbers in each of these cells are free to vary. But once you have 6 numbers set in, the other variables aren't free to vary. I know that's hard to understand. Don't really worry so much about that. But here's our p value right here. Here's our sig value. This is also our p. Look what it says. It says 0.000. That means that we're pretty much 100%. We don't like to say 100%. Let's just say we're like 99.9% certain that there are differences between these groups. Okay, what that means, remember, the alpha level would be 0.05. Our sig value, which is right here, this is our probability, is 0.00. That's much smaller than 0.05. Remember, we were willing to be wrong 5% of the time. Here, we're pretty confident we're not going to be wrong ever. We're almost 100% certain. Give ourselves a little room for error. And basically what we're saying here is this. We have found statistically significant results. We're going to reject the null hypothesis, and we're going to say that there are differences between these groups. And it's pretty clear if you look at it. What it means is people that come from upper family backgrounds or they're wealthier, they tend to major in the arts more. Okay, you can see this right here. And people from the lower classes don't tend to major in the arts very much. Maybe you can interpret that as people that are wealthy, they don't really have to get applied degrees so much like engineering. Maybe they already have money. And maybe people that don't have money, they're more likely to major in like engineering or math or something because they need to get a job. They want to ensure that they're going to have employment. So, go ahead and take a couple minutes, look at this table. I'm going to move forward, but you can always go back and look at this to clarify anything. Now, this right here is the chi-square table. This is just a snapshot of it. It's actually bigger than this, but this is what it is. So over here, you see the degrees of freedom. When you see like 1, that's telling you that you have a 2 by 2. Remember, you can't have smaller than a 2 by 2 crosstabs. So if you have a 2 by 2 crosstabs, that means you have 4 cells. That means only the value of 1 cell is free to vary. Once you know what the value of 1 cell is, the other ones are fixed. Okay, and again, I know that's hard to understand, but that's just what it means, degrees of freedom. Okay, so here are the alpha levels, 0.001, 0.01. You all know what this means by now. You don't really want to do 0.5. That means you're probably going to be wrong half the time. That's 50%. You don't want that. But let's go right here where it says 0.05. This is the most common one by far. So what this means is this. If we run a test, we're going to come back and we're going to get a chi-square value. Remember what I said before? Let's say we get a chi-square value of 4.6. And we have a 2 by 2 table. That would give us right here. So we go here, degrees of freedom of 1. This is a 2 by 2 table. We'd go right here. We would go over to 0.05. So we set our alpha level at 0.05. We have degrees of freedom of 1. Remember, if you go back and look at the tables before, I don't want to switch back and forth on the slides because it messes it up. It messes up the audio. But if you look at the SPS output, it'll tell you what the degrees of freedom are. This determines where you go right here on the left side of this. 1 degree of freedom, 2, 3, 4. Remember, the table's actually bigger than this, but this is all you need to see to understand it. So let's say you had 1 degree of freedom. You would go where it says 1 right here. You set your alpha level at 0.05. You would go across this row, and you would see 3.84. This is what's called the critical value. This is the table value. If your chi-square value is bigger than that, you reject the null hypothesis. Okay, so let's say you did a test and you got a chi-square value of 4.8. Well, you go here at the table and it says you have to get at least 3.84 bigger, and you got 4.8, so you know you're going to reject the null. Now, if you set alpha at 0.01, now we're over here. See where it says 0.01? Now we would need to get 6.6. So we got a 4.8. 4.8 is smaller than 6.6. So now we would fail to reject the null hypothesis. So hopefully now you better understand when you make these mistakes why that's called the type 1 alpha error, because it depends on where you set your alpha level. If we set it at 0.05, all we need to do is get a 3.84 bigger. If we set it at 0.01, we need to get a 6.635 or larger. So at 0.05, we would have rejected the null, but at 0.01, we failed to reject it. Okay, so again, when you run a test, you're actually going to get a chi-square value. That chi-square value will be compared to the table value, which are these values you see in front of you. If your chi-square value is larger, you'll reject the null. If it's smaller, you fail to reject. This is one reason you don't want to set alpha really at 0.5. See how here it says 0.5? Look, all you'd need is a 0.455 to reject the null. You're going to get that